So what does the AI that we all use every day have in common with the totally bizarre world of quantum mechanics? Well, it turns out a lot more than you think. The very problems that are pushing today's giant language models to their breaking point, they're actually pointing us toward a whole new frontier. A frontier where the future of AI is being rewritten using the logic of quantum computing.
To really get our heads around this quantum leap, we're going to follow a pretty clear path. We'll start with the huge scaling problem AI is facing right now. Then we'll look at a brilliant fix inspired by quantum physics that's already working. And from there, we'll take the full leap into what actual quantum computers could mean for, the very nature of language and AI itself.
Okay, so let's start with the problem at hand. The very thing that makes these large language models so powerful, their incredible size, is also, kind of ironically, becoming their greatest weakness. We are hitting a wall, a scaling wall.
Let's just put a number on this, shall we? The electricity bill to train just one model like GPT-3 was reportedly somewhere around $100 million. But here's the real kicker. That cost is on track to double every 10 months. This isn't just getting expensive, it is completely unsustainable.
And this crisis of scale, it isn't just about dollars and cents or energy. It creates some very real walls. It means you can't run these super powerful models on your phone or your laptop. And it means innovation gets concentrated in the hands of the few huge companies that can actually afford that price tag, locking out smaller labs and universities. So how in the world do we solve this scaling problem? Well, the first answer is already being used, and it doesn't even require a real quantum computer. Nope. It just requires using math inspired by quantum physics on the computers we already have.
You see, the old ways of shrinking AI models were kind of like taking a sledgehammer to them. Just randomly chopping out connections. It sort of works, but it's clumsy. This quantum-inspired approach, though, it's more like a skilled surgeon. It looks at the model's correlation space, which is just a fancy term for the complex, hidden web of relationships between all its parts, and it precisely removes only what is truly redundant, keeping that essential structure intact.
And the results are, well, they're just stunning. Using these techniques, researchers were able to chop the number of parameters in a big model by 70%, making it way smaller and way faster. And the best part? The trade-off was just a tiny 2 to 3% drop in accuracy. I mean, that is a complete game changer for efficiency. So, how does this surgical precision actually work? Well, the magic is a technology called tensor networks, a tool borrowed directly from the world of quantum physics. You can almost think of it as a kind of AI origami. It's a way to intelligently fold these massive, super complex models down to a size we can actually manage without losing their essential shape.
So what a tensor network really does is find the hidden skeleton of the LLM. Instead of trying to deal with one massive, dense block of parameters, it breaks it all down into a much more efficient network of smaller, interconnected pieces. It's all about finding that underlying structure.
The process itself is really elegant. First, you take a layer of the model and reshape it to expose its true multidimensional structure. Then you decompose it into that network of smaller pieces. And finally, and this is the key part, you snip away the redundant connections. This is all controlled by a little parameter, a sort of tuning knob that lets you find the perfect balance between how much you want to compress the model and how much accuracy you need to keep. Okay, now this is where it gets truly fascinating. The reason these quantum-inspired methods work so incredibly well is because, as it turns out, large language models naturally behave a lot like quantum systems. Their internal complexity just seems to mirror the math of quantum physics. So that begs a pretty obvious question, right? What happens when we stop just imitating quantum mechanics and we start using actual quantum computers? The whole secret sauce is the difference between a classical bit and a quantum bit, or a qubit. A classical bit is like a light switch. It's either on or it's off. A qubit, on the other hand, thanks to a wild property called superposition, can be on, off, or both at the same time. It exists in this cloud of possibilities right up until the moment you measure it. And that unlocks an exponentially larger space for doing computations. This brings us to the real workhorse of early-stage quantum machine learning, something called a variational quantum algorithm, or VQA. The easiest way to think of them as hybrid systems, a classical computer and a quantum computer working together as a team. The classical computer handles all the straightforward stuff, while the quantum processor takes on the incredibly complex calculations that would just completely choke a normal machine. This hybrid approach is really the most practical way forward for now, in what experts call the NISQ era.
That stands for Noisy Intermediate Scale Quantum. It's just a fancy way of saying that today's quantum computers are incredibly powerful, but also very sensitive to errors. They're a bit noisy. So this team-based model lets us leverage the best of both worlds, using that precious quantum chip only for the specific tasks where it has a clear, undeniable advantage.
Okay, so this is where the connection becomes truly profound. This isn't just about new hardware anymore. This is about a new way of understanding what's actually happening every single time you type a prompt into an AI.
This one idea, it changes everything. See, in quantum computing, you have to carefully prepare a circuit into a very specific starting state before you can run a calculation. Well, the theory here is that your prompt does the exact same thing to an LLM. It doesn't just ask a question, it prepares the model's vast space of possible answers. It sets the stage for everything that comes next.
Right, so if the prompt prepares the state, then what happens when the model generates the next word? Well, that's the equivalent of a quantum measurement. Before that word is chosen, there's this huge wave of possibilities. The act of generating the word collapses that wave into one single definite outcome, the word that pops up on your screen.
So just think about that for a second. Every time you use an LLM, you are, in a very real sense, acting like a quantum engineer. You are preparing, and then you are measuring a complex semantic system to get your answer. Pretty wild, huh?
Okay, let's tie this all together. What does this incredible convergence of language and quantum physics actually mean for the future? Where is this all heading? Well, it looks like we're really looking at two parallel futures. The first one is happening right now. These quantum-inspired techniques are giving us extreme efficiency, smaller, faster, cheaper models. The second is on the horizon. True quantum hardware promises a whole new level of expressivity, allowing AIs to capture much deeper correlations and potentially unlock capabilities we can't even imagine yet.
But maybe the most mind-blowing idea of all is this. What if these quantum techniques work so well because human language itself is fundamentally, well, quantum-like? With all of its nuance and its ambiguity and all its layers of meaning, maybe language already behaves like a quantum system. We aren't forcing language into a quantum box. We're just realizing it might have been there all along.
And that's the final thought I really want to leave you with. If this new quantum lens works for the profound complexity of human language, what else can it help us understand? We're not just building better AIs here. We might be on the verge of discovering a fundamental new toolkit for making sense of complexity itself.